Thank you very much for the introduction and for having me here today, starting the Linux Science Day by talking about ultrafast science. I'm from the ultrafast group in Denmark, and we deal with dynamics that are induced by light. These kind of dynamics we are looking at might be the contraction of molecules, it might be molecules breaking apart or just changing bond length, but it can also be something that happens not to the molecule itself, but around the molecule, because we are looking at molecules in solution. So it might be also a solvent rearrangement due to a light-induced process. I will start with talking a bit about what kind of timescales we're interested in for these processes, then talk about the technique we're using at DTU for looking into these processes, which is solution scattering. And then I will give you 3 examples of recent studies. So the idea what we want to do is we want to study chemical dynamics. We're interested in those because they are an important part if we want to further develop materials for energy harvesting, for memory devices, so some kind of molecular switches, and also for batteries. So the overarching goal for us is to understand the function of materials by characterizing them while they function. So we want to look at them while they're actually doing what we want them to do, which necessitates us looking at them on the timescales they're working at. And if we think about the timescales that are necessary here, we can think about the size of an atom, let's say about an angstrom, and about the speed of an atom, which we can approximate with like a kilometer per second maybe. And then when we think about an object that is the size of an angstrom, how long does it take for this object to move on the scale of an angstrom? Then we get to time scales of about 100 femtoseconds. So this is the kind of time we need to look at if we want to learn something about the chemical dynamics in materials for energy harvesting or memory devices. The technique, as I said, that we are using is scattering. So we look at the scattered light and thereby learn something about the geometry of these systems. That is a pump probe approach, where we have a laser pump to excite the system and an X-ray probe that then scatters from our sample, which is in a liquid environment, a liquid jet in this case, and then scatters into a 2-dimensional detector. What we then get is scattered intensity as a function of the scattering angle, here written as Q. And as this is mostly symmetric, we can often do an azimuthal integration and get from a 2-dimensional detector image to a 1-dimensional scattering per scattering angle curve. This is nice and good, but gives us also some challenges because we have our sample in a liquid environment. So if we look at these kind of curves for example, a molecule like iron hexacyanide in water, that looks very, very similar to the scattering from a molecule like iodide in water or just water itself, because most of the molecules that scatter in a liquid jet will be water, right? So we have to still get somehow to the information of what the molecule actually does when we excite it. And the trick in order to do so is to use different scattering. What we do in there is that we measure 2 times actually, once without exciting it, so with the laser off, and a second time while we excite the system. And if you then subtract those 2 scattering information from each other, you will get a measure of the laser-induced changes in the system, and thereby only look at what you did to your molecule by exciting it with a laser. So now we have different scattering delta S, which is a small signal, but the nice thing is we can change also the approach on the timing between laser excitation and probing with an X-ray, and thereby more or less do a movie of what happens to the system over time by varying this time between those 2 pulses. Now, the only thing left to learn is how do we interpret these kind of different scattering signals, because they're in Q space, not in real space, and therefore we have to do some simulations, and in our case, that's molecular dynamic simulations to learn what kind of features in this different scattering translates to what kind of molecular changes, to what kind of geometry changes. We can do so. We have to take into account multiple parts, because if we excite the system, we will have changes in the solute, we will have changes in the bulk solvent, and also the third part we have to take into account is that the solvent molecules close to the solute might interact different than the bulk solvent in total. So these contributions are calculated and then compared to our measurement in order to learn something about the system. Coming to the example, the interesting part where we look at the science that happened over the last years. The first example I brought today is of the molecule that is iridium diamond, which is the molecule you can see up here, has 2 iridium atoms. And we know from simulations that upon excitation with a laser, this molecule contracts so that the iridium atoms come closer to each other. We can actually measure that, and the example you see here was something that was measured at the synchrotron in Grenoble at the ESIF, where you see in black the measured data, and then below that the different contributions I just showed you before from the solute and the solvent, which we add up in a linear combination model, and then build a model that in this case really well fits the data that was measured. And from the simulations and the comparison, we learned that the contraction of the molecule is actually on the scale of 1.4 angstrom. This is nice and good. The question is that the end of the story? Is that all that the molecule does? And if we look at, for example, transient absorption spectroscopy down here on the time scale of 100 picoseconds, it looks like, yes, something happens and then goes away after 100 picoseconds. But if we zoom in on the first 3 picoseconds of this signal, you will see that no, just contraction is not the end of the story, and there's a lot more happening in the whole system upon excitation with light. So what is actually going on here? What else could happen? And what I show you here is so far only theoretical simulation done by Asmus Stone, who looked at what else might happen next to the contraction. And he figured out that it's not only contracting, it's also that if the molecule contracts, there's less space for solvent within the molecule, so there's a desolvation process within the first few picoseconds. There might also be a twist of the molecule, as well as a reorientation or coordination of the surrounding solvent after the contraction happened. So all of these different processes give different signals in the different scattering that we hopefully will be able to disentangle from the measured signal in the future. The second example I brought today is of aqueous halides, who are interesting for things like atmospheric chemistry, where seeded processes happening when, for example, clouds form, or also in biochemistry with transport through membranes. And the big question we ask here is, can we figure something out about the process when we excite the halide, which is a charge transfer to solvent state process? So the iodide gets excited and ejects an electron into the solvent. But where does the electron go to? Does it become a free electron? Does it become a contact pair? How far does it go? And the thing is, with our technique, we don't really see the electron itself. We only see structure, right? But we can use the technique still, because if the electron is still at the iodide, then the water surrounding it in the first solvation shell is more or less structured. This is the structure we can see. After ejecting the electron, the structure will be lost, or at least lessened, and this change in the structure of the water is something we can follow. You see some data on the right of the slide here for the first tens of picoseconds after exciting. And we see it's a very fast change. You look at the blue and purple dots after excitation, where the water loses its structure and then it comes back. We can fit this process and derive from the time how far the structure comes back. And by assuming that it's a purely diffusion-driven process, how far the electrons actually ejected. In this case, the result was about 5 angstrom. That's of course a distribution because not all electrons go to the same distance. Some stay closer to as a contact pair, some might go further out. But these are processes you can also look into with the technique. The third example is the closest to application, which I thought might be fitting for a new materials talk, where it's about photosensitizers. There are dye photosensitizers that work. We can use them to get charged. When we have, for example, a ruthenium-based dye, you can excite an electron from the metal center, from the ruthenium, into a ligand, and then use this process. It stays for around a few hundred nanoseconds to light up your light bulb. The thing is, ruthenium is scarce and pretty expensive, and it would be super cool to change the ruthenium to something more available and much cheaper, for example, iron, which is, if you look at the periodic table, very close to it and should have similar effects. And in fact, you can make an iron-based dye that also has an electron, which upon excitation goes from the iron center to a ligand. The only problem with that is that the iron in the electron in the ligand does not stay there very long. After about a nanosecond, it has already decayed back into the ground state, which means we do not have enough time to actually use this electron in the excited state for any kind of application. The idea is now to hopefully in some way tune the states of our molecule to be able to use it for applications. So what we first want to do or need to do is to understand the pathway through the different excited states that the electron can do, and then hopefully in some way alter the shape of these states. What you see here is the potential energy landscape going from the ground state in black first up into the ligand, that is the red one, the metal to ligand charge transfer. And then we know the electron goes somehow through metal-centered states where it's still excited before going back to the ground state. We also know that the solvent can have a big effect on these kind of pathways. For example, if we look at iron cyanide in water, this is a very poor photosensitizer because we have a low-lying metal-centered state. So it's easy for the electron to fall back down into the metal-centered state, and therefore it's only very short-lived. On the other hand, if we have the same molecule in another solvent, in methanol, for example, it's a better photosensitizer because the MC state or the metal-centered state is higher lying, therefore harder to access, and the process takes longer, and we have more time to use it efficiently as a photosensitizer. With that, I come to the conclusion in the end. I showed you something about the sensitivity of the solution scattering technique, which if you apply it at synchrotrons or especially at free electron lasers, you have the time resolutions to look at chemical dynamics while they happen. And these techniques are very strong, especially combined with spectroscopy techniques like absorption or emission spectroscopy, where you learn more about each of the states of excited states. There are many people working on that. I'm from the University of Denmark, but it's a huge collaboration with many people and many facilities. Hopefully in the future also with Femtomax here in Lund. So I'm looking forward to that and want to thank you for your attention.